Hello, welcome to Math 204. This is section 2.5, Power Series. Power Series! Power series are like infinite series, but they have a functional dependence. So they're not terribly different from anything that you know, but they are power! So, you know. Seriously though, the power series are cool stuff, and they're going to come up again and again. You've seen them before doing real analysis in the terms of Maclaurin and Taylor series. So a power series is a function which in this class we'll denote by an S of the form S of z is equal to the infinite sum from n to 0 to infinity an z to the power of n. So suspiciously like a Taylor series or a Maclaurin series. First term a0, z to the 0 is 1, so it's a0 plus a1z, a2z squared, and so on and so forth, where for all n, an is a complex number. A power series, so these definitions are going to be things that you've seen before. A power series converges at a inside the complex numbers if the series SA equal to sum n equals 0 to infinity. Sometimes I'm going to leave the bounds off because they'll be implied by the context. A to the n converges. So this is a function. S is a function. This is the form of the function. That's an equation that represents the value of the function at z. And this is a real number. A complex. Sorry, this is a complex number. Well, it could be real, but a complex number definitely. So this is the distinction between these two things. This is an equation for a function evaluated at the point z. This is a complex number. It is the value of the function s evaluated at a. So what does this mean? This is the same as saying that there exists some L inside the complex numbers such that for all epsilon greater than 0, there exists some number L, and I'm going to put an A in there as well because this can depend upon the choice of the point that you're evaluating at, so that k bigger than n implies that the partial sums, remember the partial sums, converge to L, or at least are epsilon close to L. So this is the definition of convergence of a sequence, of a series, in terms of the sequence of partial sums. So you've seen that before. Importantly, n depends on L and A, or at least can depend on L and A. So if you remember from class when we've been doing epsilon delta things so far, all of the choices that we've made for the delta have been allowed to depend upon the limit point. Here they're also allowed to depend upon the point that we're evaluating at, which actually I think we've incorporated that when we did some of the proofs about continuity of composition of functions. Okay. So this has a particular name. And it reflects this dependence here. That name is called pointwise dependence. So the point being that the convergence of the series can depend upon the point at which it's evaluated. There is another way for this to work, which is So what I want to rewrite this to avoid talking about the limit L, mainly because that's going to come up in a moment. So rewrite. I'm going to do it in terms of Cauchy convergence. Cauchy convergence allows me to talk about properties of the sequence. It means I don't have to mention the L function, the actual limit point here. So for all epsilon greater than 0, there exists a natural number and I'm going to put epsilon in there as well, and epsilon really could have gone in here too, but anyway, there exists an n which can depend upon epsilon and a greater than 0, so that m and k bigger than n implies that the distance between the partial sums is getting increasingly small. Sorry, that's not infinity, that's a k. Again, so we're saying that the sequence of partial sums, when evaluated at A, is Cauchy convergent, and this is still pointwise convergence because we have the dependence on A. So this allows us to talk about uniform convergence. A power series is uniformly convergent, or some people would say converges uniformly, because there isn't enough scope in mathematics to be confused already, on an open set, which I will call E, subset of the complex numbers. Okay, this is the definition. If, for all epsilon greater than 0, there exists a natural number which depends upon E, the natural number depends upon epsilon only, so that for all E inside our open set, M and K bigger than N implies that the partial sums are Cauchy convergent. Well, are epsilon close, I should say. Oops, and that's an E. Okay, so this is really, really important. And the distinction can be a bit confusing. So, in this definition, I had A beforehand. This is saying that the sequence converges at A. This is saying that the sequence converges for any E inside our set, capital E. But it says more than that. What it says is that there is an N that works for any of the partial sums evaluated at any of the points in the set. This says that convergence will happen at A. It says nothing about convergence at nearby points. In particular, it says nothing about how N might depend upon A. In this particular case, this says that N has no dependence on A. One way to interpret this statement is that convergence of the power series evaluated at points in E, let me rephrase it, say, for any point in E, the power series converges at the same rate as the power series evaluated at any other point in E. And that's because the n, which describes the rate of convergence, because n tells you how far along the sequence do we need to be in order to ensure that the difference of the partial sums is less than epsilon. So this is really saying that n can be chosen to work for any of the elements in our set, whereas this says that n is chosen only to work for one, the element A. Point-wise convergence versus uniform convergence. Uniform convergence is a very important concept in mathematics, and in complex variables too, of course. Very important. An example: sum Zn from n to infinity, 1 plus z plus z squared plus so on. So if z is not equal to 1, then the partial sum right, and that follows from geometric series, which we proved in class, I think, in the tutorial. Alright, and this form tells us that the limit, I'm going to call this the partial sum, sk minus 1, the limit of the partial sums is, we can distribute above and below, the limit of zk over the limit 1 minus z. The limit of the bit below is just 1 minus z. The limit of the bit above, well, not certain. So if the modulus of z is less than 1, then that tells us that the limit of zk goes to 0. Prove it. And this tells us, of course, that the limit of the sk minus 1 must equal 1 over 1 minus z, which is also the form of the geometric series that we've seen before. And of course, this implies that the infinite sum of the Zn is equal to 1 over 1 minus z, which is great. If the modulus is greater than 1, then the nth term test, sorry, it took a little bit of time to get there, nth term test implies divergence. And if the modulus of z equals 1, you should have a think about it. You should have a think about it. My claim is that this will diverge. But you should try and prove that. Right, now we have a very important theorem which will crop up again and again and again. So pay attention. This is going to matter. Okay. For each power series, there exists an r inside the positive real numbers and possibly 0, so that for all z, the modulus of z less than r implies that S of z converges absolutely. which is rather nice. The series converges uniformly, which is also kind of nice, on every closed disk of the following form. The modulus of z has to be less than or equal to r, where r is strictly less than capital R. And 3, the series diverges for all z where the modulus of z is bigger than r. And of course the theorem doesn't say anything about what happens when the modulus of z is equal to r. But yeah. And, now this is important, 1 over r is equal to the lim sup as n goes to infinity of the square root of n a n. This is called Hadamard's theory, Hadamard's formula. Not the whole theorem, just specifically this equation. Right. Now the proof of this, if my memory serves me right, relies on the root test, which we haven't seen. So I'm going to give you a few facts about this, and I'm going to talk about the root test, and then I will give a hand-wavy explanation for why the proof works. Okay, so a bit of a break there. I'm back, and I can't remember what I was talking about, so I'm just going to keep on going. Power series. R is called the radius of convergence. Basically because the sequence converges. The series converges when evaluated on some point whose modulus is less than r. So, oh gee, that's not the real numbers, that's just r. There you go. Right, So the circle with radius r in the complex plane is called, perhaps unsurprisingly, the circle of convergence. Though it's worth pointing out that the modulus being equal to r doesn't really imply anything about the actual convergence, so everything inside the circle. And you really need to check what happens when the modulus is equal to r for particular points. Okay, now I need to tell you what lim sup is, so let Zn inside the natural numbers be a sequence. Then the lim sup of n goes to infinity of the sequence. Well, there's two different ways to write this. There's multiple different ways to write this. The limit as n goes to infinity of the supremum of zi I greater than or equal to n. So this is the supremum of the sequence where you're chopping off some finite number of elements at the beginning of the sequence. So, you know, the first element of the sequence could be absolutely massive and huge, and the rest could be really close to 0. Well, lim sup will be really close to 0, because we're taking the limit as n goes to infinity of the supremum of all the elements equal to and beyond the nth one. So we'd eventually end up forgetting about big ones that stand out by themselves. And this is also happens to be the infimum of the supremum of the zi, so I greater than or equal to n, for n greater than or equal to 0. So take all of the supremums and take the smallest one. smallest upper bound eventually. So one way to think of this is the eventual smallest upper bound. Of course, this doesn't make a great deal of sense for complex numbers, so yeah, we need these things are real, modulus real. Why does it not make sense for complex numbers? Something to do with size, which we talked about a lot. Lim_sup and lim_inf don't come up very often. Lim_inf is the same thing, but with imps instead of sups, and switch stuff around. So they don't come up often, but they are important concepts because they say something about the long-term limiting behavior of the sequence. Okay, root test. There are too many O's. Suppose Zn, subset of complex numbers, is a sequence of complex numbers. And the lim_sup as n goes to infinity of the square root of n of the absolute value of these things is equal to some number which I'll call L. If L is less than 1, then the sum of the sequence is absolutely convergent. And if L is greater than 1, then the sum is divergent. And as usual, we don't know what happens when L is equal to 1. The proof of this follows is the same as the ratio test, and you should realize that this is very similar to the ratio test. So the proof of our theorem about the radius of convergence follows along these lines. We're going to let alpha n equal an zn, and we take the lim_sup as n goes to infinity of the absolute value of the alpha n's, which is equal to the lim_sup n goes to infinity of the absolute values of the an's times the modulus of z, and that's going to be equal to the modulus of z over r. So if, which can be rewritten as, surprise, we get absolute convergence, and which can be written as, we get divergence. Okay, and the proof of uniform convergence is left to you. Uniform convergence proof left to you. And it's important to try these things. There's lots of practice examples in the notes. There's lots of things that during lectures I've left to you to try, and you should try them. If you want a good mark, this is one way to do it. I mean, there are of course other ways to do it as well, but doing the practice is making sure you can write down these proofs and understanding these concepts. Putting in some work will help. I promise it does. Anyway, proof left to you. It's not so hard, but there's a bit of detail involved, but it's all based around the same kinds of ideas that you've seen all already. So it'll be good practice. Do another example, one that will be important soon. The series Z, infinite sum power series, is absolutely convergent. for all z inside R. So the radius of convergence is infinity. Proof. We're going to do this one in detail. Let z be inside complex numbers. Let n be a natural number so that n is bigger than 2 times the modulus of z. Then, if little n is bigger than big N, we have the following. Z n plus n over n plus 1 factorial is equal to 1 over n plus 1. I've just taken out one of the components of the factorial, and I take out one of the components of the modulus, and I end up with the modulus. I don't need, well, let's say I don't need this. Note. As just a calculation, if n is bigger than n, which is of course bigger than 2 times the modulus of z, then the modulus of z is less than n over 2. So zn plus z to the power of n plus 1 over n plus 1 factorial is less than or equal to, and here we start working this stuff out. N over n plus 1 over a half. The n over 2 comes from here, and that's the n plus 1. Zn n factorial, and that's less than, well, this is less than 1, so that's less than a half Zn over n factorial. Therefore, for all k greater than 0, Zn to the k, z to the power of n plus k, over n plus k itself, plus 1, factorial, is less than or equal to 1 over 2k, Zn over n factorial. So, the sum from k equals n, capital N, to uppercase lower n is z. Now I'm looking at absolute convergence here, so we're taking the modulus, is less than or equal to the nth term. Oops, I've written it all wrong. There we go. 1 plus a half squared plus all the way up to little n minus big N. And this is less than or equal to 2 so proving that this is less than 2 is really just taking n to be very, very large. This sequence converges to 2. And you can use geometric series, I suppose, for the real numbers to prove this. This term goes to 0 as n goes to infinity, and that implies that the sequence of terms, the sequence of partial sums, is Cauchy. And that implies convergence. Because we're talking about partial sums of the absolute, of the modulus of complex numbers, this implies that the series is absolutely convergent. As is needed. You should prove this. Okay, lastly, a slightly more definition of a power series is a power series about z0 inside the complex numbers is a function sz equal to the infinite sum a n z minus z0 to n. And everything that we've seen so far works exactly as for this. And that is power series. Important. And that is page 6.